So for second lecture, just let us talk about statistical representations, which is basically the Bayesian network. So let us just define what is a generative model as a statistical model, and representing probability distributions, Px. For example, if we have a 10 by 10 grayscale images, you just convert these images to from here to here to here to here. You just put these pixels. So these pixel value to be one-dimensional n by n. Here, 10 by 10 vectors. This is a pixel vector. And we just try to get and let us define this vector to be x. So this vector x is n by m pixel value vectors. Here, in this case, it's 100 vector values for grayscale. So for RGB vectors, you have to multiply RGB values. So you have a RGB vector as x1, x2, x3, and you have a x3n vectors. So what generative model generate is probability of this pixel value vectors. So let us just talk about how we should represent these probability distributions as Px. And we talk about the class of the dimensionalities and crash course on graphical models. That's we discuss these as a Bayesian network, Bayesian network. And we discuss about generative and discriminative models. It's like the relation between the generative model and discriminative model is like inverse. And we discuss a little bit about neural models. Okay. So first of all, let us discuss about the discrete distributions. For example, here is a 0-1 coin flip images. These are so-called Bernoulli distributions. So heads or tails. So specify Px heads equal P and else tails 1 minus P. And this is a Bernoulli distributions, and the samples a biased coin toss. And other is, for example, the m-sided dice. So you have M side with 1, 2, 3, or 4, 5, 6, 7, and each side has probabilities, and P1 to Pn should be 1, and these rolled dice with biased probabilities, we get categorical distributions. And for example, we want to talk about black and white images with figures. And this is a 0, 1 black, white Bernoulli random variables with n by n. So we have n by n pixels here, black and white. So how many possibility of these images? That's simple. If we have n pixel, we have a 2n possibilities. So we have n pixels. So we have a px1 to pxn joint distributions. And how many parameters to specify these joint probabilities? We discuss this later on. However, that's 2n minus 1. Okay, anyway, so you can look for certain textbook or something. Why you have a minus 1 here? However, anyway, we derive this later on. Okay. So if each pixels are independent, this joint distribution can be px1 multiplied by px2. So these are each pixels. px1 multiplied by px2 multiplied by px3 and multiply until xn. So how many possible states? That's a 2n, 2 power n. And how many parameters to specify the joint distribution? How many to specify the marginal distribution of px1? That's 1. So 2 power m entries can be described by just n numbers. So independence. So anyway, these each pixels, if they are independent or not, if you assume all independence is a little bit too strong assumptions. However, if they are independent, we have pxi I equal 1 to n multiplication. So we need to think about important rules. So first of all, chain rule is very important. So you have a black and white images. With S1, S2, S1, S2 state. So this is a joint distribution. PS1 cap S2 cap 2 until cap Sn. And what chain rule tells you is you get PS1, then you have to multiply PS2 after S1. And this continues to PSN after S1 cap until Sn minus 1. Okay, so this is a chain rule. Another important rule is Bayesian rule. Let S1, S2 be event, and PS1 larger than 0 and PS2 larger than 0. PS1 after PS2 can be represented by PS1 cap S2 divided by PS2 equal PS2 bar S1 multiplied by PS1 divided by PS2. So this is the famous Bayesian rule. And anyway, you have to remember these Bayesian rules to discuss about your models. So structure through conditional independence. So as I told you that all independence is too strong. So you have a chain rule to represent your images, n by n images. So chain rule gives you this multiplication of all pixels. So for this, how many parameters you need is 1 plus 2 plus continue 2 plus 2n minus 1. So because these are parameters, you get 2n minus 1 parameters to represent this chain rule. And you need these parameters. So Px1 requires 1 parameters. Px2 bar x1 equals 0 requires 1 parameter. And x2, x1 equal 1, px2 bar x1 equal 1 requires 1 parameter. And total 2 parameters are necessary. Thus, you need 2n minus 1 parameters. However, this still you need exponential 2n power, order 2n power. And this is something expensive. So now we suppose xi plus 1 and x1 to xi minus 1 is independent. So this is Markov. So x plus 1 is only dependent to xi. This is the Markov model. So go back to chain rule. So px1 multiplied by px2 bar x1, px3 bar x1, x2 until pxn x1 to xn minus 1. However, we neglect x1 and this part. So this is Monte Carlo. Okay. And this, okay, Monte Carlo, no, not Monte Carlo, Markov chain. Markov model. So now your model depends only on your previous results. And then you get this chain rule. And how many parameters you need here? That's 2n minus 1. And your model is now reduced from 2n, 2 power n minus 1 to 2n minus 1. And this exponential is reduced. So this model, conditional independence model, is okay. And let us think about the general idea of Bayesian network. Use conditional parameterizations. That's a Markov chain. Markov model. So you have a px1, px2. So process goes one by one. And only depends on x2, only depends on x1. x3 only depends on x3 only depends on x2. So for each random variables, specify px1, pxi minus 1, and px minus 1 of random variables. And oh, okay. And you get joint parameterizations. For example, here, pi I to n, pxi bar. This is generalized. I minus 1. And we need to guarantee phi is a legal distribution. And this multiplication has to correspond to chain rule factorization with factors simplified due to assumption of conditional independencies. Next, let us think about the dielectric acyclic graphs. That's a dark model. And this can map to neural networks. Okay, so you have a graph model. So each node belongs to V for each random variable xi. And we assume the conditional probability distribution CDP per node. So you have this conditional probability model. Okay. And each graph is called the structure of the Bayesians. And this dark graph network can be written as this one. So you have a sum. So each probability only depends on your connected neighbors. So if you say xy, xpai is here. So these are only conditional. And now px1 to xn is a valid probability distribution because ordering implied by a DAG model. And this is economical representations and only exponential in PAI1, not graphs. So this you can reduce your parameters from exponential to n. So this is a direct cycle and the DAG model or something like that. And we discussed this in neural networks, okay? This is, we also consider the following Bayesian networks. So each models have conditional probability in each node. So this can be represented by only the connected multiplication of your probability with only connected probabilities. Okay. So Bayesian networks. So Bayesian network structure implies conditional independencies. So you have such network structures and DIG. Okay, so this is a D, node D, this is node I, node S, node G, node L, DIGSL node. And we call this Bayesian network factors. We have a PD, PI, PG, PID, PS bar I, PL bar G. However, by chain rule, these can be rewritten to PD, PI bar D. So you have this one to this one. So PG depends on D and I. PD depend on D after I. Yeah. D after I. And okay, so these relations. And PG after ID multiply by, wait a minute, yeah, PS IDG, PS IDG, and also PLGDIS. However, D and L so are independent because you have a two. This is not directly connected. And also S is independent with DG and L. And L is also independent of IDS also. Wait a minute. IDS also G. Okay. So you can use these conditional independent relations to represent Bayesian networks. So Bayesian networks given by GP, where P is specified as a set of local conditional distribution associated with G's node. And Bayesian network is efficient representation using a graph-based data structure. Computing the probability of any assignment is obtained by multiplying by conditionally probabilistic distributions. So if you have a network, your probability is only determined by your connected node. Okay. And can sample from the joint by sampling from the conditional probability distribution according to dark ordering. Can identify some conditional independence property by looking at graph properties. In this class, graphical models will be simple, only 2 or 3 random vectors. So next we discuss about the generative, discriminative, and some functional parameterizations in statistical models. Naive Bayes model for single-level predictions. So let us now think about classify your emails as spam or not spam. Y equal 1, y equal 0. So let 1 n index the word in our vocabulary. So also xi equal 1 if word I appears in an email and 0 otherwise. So specify some words in our vocabulary and let it be 1, and if word I appears in an email, let xi to be 1. And emails are drawn according to some distributions. So if you have a x1, these are each is certain words in the list. And if these words in the list, you get y equals 1, the probability of the spam. So, and these words are conditionally independent, given y. So, you have a future words vectors, and these future vectors are given. You have a connection from y to x1 to xm. And you can represent this probability py and the joint probability of x1 to xm. So you can multiply py with pxi bar y and all multiplications, you get Bayes statistics for single level predictions. And other example, for example, naive Bayes for classifications. Classify emails as spam or not spam, y equal 1 or y equal 0. Let 1 is the n index, the words in our vocabulary. Okay. And xi equal 1 if words I appear in an email and there otherwise. Emails are drawn according to some distribution py x1 to xm. Suppose the words are conditionally independent given y, then this can be represented as py multiplied by, this is a chain rule, y xi bar y and all multiplications. So estimate parameters from training data, predict with Bayes rule. So what you get here is all multiplications, okay, here with py, okay, and I equal 1, okay, and py y and px y, you multiply by py equal 1, you multiply by py equal 1. Okay, so this is a simple Bayes rule. So the question here is, are the independence assumptions made here reasonable or not? This is a little bit difficult to answer. However, the philosophy here is nearly all probabilistic models wrong. However, many are nonetheless useful. So, using this Bayes rules, if you want to classify if your emails are spam or not, if you use this conditionally independent models, maybe nearly all probabilistic models are wrong, but still you can classify many, exclude many spam mails. So that makes this Bayes rule useful. Okay. So next, let us think about discriminative versus generative models here. So we have a chain rule, and we have a probability of y with joint distribution x. The chain rule gives you px bar y multiplied by py, or py bar xpx. So what this means is that, so these are conditions, and this is a input. So you give the input y, discriminative, certain words. You get image vector. This is a generative model. So giving images, X vector, you get the classification of the images, cat, dog, car, or something like that. This is a discriminative model. So suppose all we need for prediction is py bar x. This is a vector, image vector. In the left model, we need to specify learn both py and px bar y, then compute py bar x using Bayes rule. In the right model, multiplication satisfies to estimate just conditional distribution py bar x. We never need to model learn use px. And we call this a discriminative model. So right-hand side model. Here, we never need pxy. And this is a discriminative model. And the multiplication of all probability is only used for discriminating y's label. Okay, so we can write this using neural networks. So since x is a training data or random vector, chain rule will give you pyx to be chain rule. Py, px1 bar y, px2 bar y, x1, pxn y, x1, xn minus 1. Also px1, px2, px1, px3, px1, 2, py, px1, pxn. Okay, this is just a chain rule. So for generative model, you give a cat, word cat. You generate image pixels, and these are anyway. These are chain ruled here, and also these are chain ruled here. And discriminative model gives you image vectors. You give a cat or a dog. So we must make the following choices. In the generative model, py is simple, but how do we parameterize pxi bar paiy? Anyway, this is the choices. So what's images you have to give? And in discriminative models, how do we parameterize py bar x? So if you give a cat image, you get cat. Here we assume we don't care about modeling px because x is always given to us in classification problems. Okay. So anyway, generative and discriminative is inverse. So you just give simple py to generate px after you give y. And in discriminative models, and there is certain conditionally independent relations for each pixels. After you give x, you get y. This is a discriminative model. And we don't need px modeling because x is always classification problem. Okay. Anyway, this is very important because in generative models, we need models of px. And this is usually, this distribution is not known. And we need to discuss this later. So naive Bayesian models for generating models assumes x and xi given y is independent. And this becomes a Bayes model. Okay. And usually to train the neural network, you need to use logistic regressions. So you have a parameter alpha and data x. You need to classify your probability to be 1, y equal 1. And this is yxa functions. And these functions is sometimes sigma functions, or sometimes you call this logistic functions. So in DAG model, we represented them as a table, probabilistic table. And for logistic model, there is many data. So that we want to represent this table as fitting to certain functions. And we usually use this logistic function, 0, 1. And we assume the linear dependence for z alpha x, and py equal 1 x alpha equal sigma z ax. This is a linear dependence. And logistic dependence is sigma z alpha x, and sigma, okay, so you have a input and you get y. And after you get y, you put this z into alpha sigma, and this sigma function is logistic function. Anyway, if you learn the basics, very basics of the neural network, you learn these logistic functions. So logistic regression, so this is a linear dependence, and this is logistic functions, and what you do is just fitting. To train your model data. So logistic functions will give you 0 and 1. And what this means is that you have many input here, and this corresponds to 1, y equal 1, py1, py0 after x, input of x. So decision boundaries is 0.5 larger than p larger than 0.5, and this is linear, almost linear in this slope. And we discuss about equal probability contours are straight lines, and the probability rate of change have very specific form. That's a third plot. So try to find these distributions. Is learning, how to say, you need to train your neural network. And actually, for classifications, discriminative model is very powerful. So you have generative models. So you give a y equal 1 or y equal 0. You generate a vector x, maybe this is image. And for discriminative one, you give a image or data. You get y equal 1 or y equal 0, cat or dogs. And the logistic model does not assume xi and xi minus I is independent after y. And this does not assume these relations. Unlike Bayes' rule, this makes a big difference in many applications. For example, in spam classifications, let x1 equal 1 blank in image and x2 equal 1. For example, you have an account word in the email. So blank, the word blank in the email and the word account in the email, both you can give this classified as spam. Regardless of whether spam or not, these always appear together. x1 equal x2. learning in naive Bayes result in px1 bar 1 y equal px2 bar y. Thus, naive Bayes double counts the evidence. So you have x1, x2, with the word blank and count. These both can be classified as spam mail. And learning with logistic regression sets alpha 1 equals 0, alpha 2 equals 0, and ignoring other multiplication of the probabilities. So 0, 1, 0, 1. So the detailed other conditions are all neglected. So how to say? Anyway, this is Bayes rule. And Bayes rule is powerful. However, can double count the evidence. So this means not always you can classify these your emails. The classification of spams or not spams is not always correct. However, still Bayesian rule is useful. And also, generative model is useful. So using chain rule, you get, you give a was cat, and you can generate images X. And this chain rule gives you px bar y py multiplied by equal p. This is a chain rule. Py after bar x, you get multiplied by px. So these are the same. However, inverse. This is a generative. This is a discriminative. And you have a neural network here. You have a neural network here. And this is a statistical model. Using a conditional model is only possible when x is always observed. When some xi variables are unobserved, the generative model allows us to compute py bar x evidence by marginalizing over the unseen variables. So this is questionable. Okay. So you generate an image space or manifold with many images with probabilities. However, the question is that you trained this space with specific images. And if you have xi, which is not observed, however, still these images define a space manifold, which includes images not exist here. We call this marginalizing over unseen variables. So we do not know if this is correct or not. However, still useful. And indiscriminative models, and these we have to use a neural network to train. So in discriminative models, we assume that py equals 0, and you have a parameter alpha, and you have a condition x, and you get fxa, and the linear dependence, non-linear dependence, logistic models you train. So what you have to do is you train these parameters. You train these functions by using your neural networks. And p neural y equal 1, and this is the training data. X is training data. And you get sigma here, and you just try to obtain optimizing ABA in your neural network. Okay, so what you have to do is just you train these parameters in your neural networks, in your neural network models. So in discriminative models, we assume that y is certain, and you use these data parameters to train. And these f can be linear dependence or logistic functions, and just what you have to do is just train these parameters. And the nonlinear dependence, whatever you like, you get certain functions to train. And what you have to do is just you train your neural networks here. And the Bayesian networks and the neural models, and these are the same. So you have a okay, these are the variational. Variational means it's that all the parameters, we determine all the parameters with probabilities. And Bayesian networks is conditionally dependent. It's a Markov chain. It's a Markov chain. So px1, px2, x1, px3, px2, and px4, px1. These are okay. So it's only dependent on previous one, and sometimes you call Markov chain. And assume conditional independence and neural networks, you get these models here. So assume specific functional form of the condition S. A specific deep neural network can approximate any functions with this conditional independent Bayes network. So now finally we discuss about continuous variables. So now P x is distribution functions. So this is distribution functions. And probability. So you have to multiply infinitely with this conditionally independent relations for Bayes rule. However, we cannot represent this function as a table anymore, and we can use a Gaussian, which is this is a little bit incorrect here. 2 pi sigma here, and exponential minus x minus average square divided by 2 sigma square. This is a normal distribution, Gaussian distribution, and this is uniform distribution. So we can assume many probability distribution functions in Bayes network. If X is continuous random, we can usually represent multiplication of a joint density probability functions. For example, for Px x, you get multiplications. Okay. So this is vector functions. So these are the vectors, and sigma is vectors, and average is vectors here. And so anyway, this is a joint probability. So x1 of the Gaussian distributions. So, and also the chain rule is still the same. I think that's it. So for continuous variables, so with vector variables, so this is like an image, and so you can assume Gaussians, and for vector Gaussians, still this is, you can assume, but x is vector, and to get the n-dimensional, if your vector is n dimensions, n-dimensional Gaussian. Okay, and still Bayes rule still can apply. So continuous variable problems, you have a Bayesian networks with continuous variables, f distribution functions, probability distribution functions. Usually people use a mixture of two Gaussians, or Bernoulli, and Bayes is factorizations and variational autoencoders. There is many continuous variables probability distribution functions, Gaussian mixtures, and Bayes network with factorization still works, and variational autoencoders still works. So these are